Discovery's 4 computers now have primary control of critical vehicle functions.
Discovery, roger. Go for deploy.
Recommend vector transfer to the BFS.
Roger, 0J, and I feel fine. Capsule is turning around.
Mars, the first step in colonizing space. Whilst space travel has made exceptional progress over the last century, it was only in July 1969 that man first walked on the moon, and now just 50 years later there are plans to send the first humans to Mars in the not-so-distant future. According to NASA, they plan to send humans to Mars by the year 2033. There have been several missions that have landed on Mars. The United States has successfully landed 8 on the Red Planet, including Opportunity and Insight. While the spacecrafts have conducted exceptional research on the planet, it's not the same as having humans exploring the area. Although it's exciting to think about humans landing on Mars, they will encounter numerous problems during their exploration of our planetary neighbor. From long-lasting dust storms and exceptionally high radiation levels to worrying about their food supply and their overall health. They'll have huge obstacles to overcome, not to mention the extremely long trip there and back. Let's look at the most challenging obstacles the astronauts will face on their journey. Mars may still be volcanically active. A new study shows that Mars may very well be volcanically active. Nobody's seen direct evidence of volcanism. No eruptions or magma or anything like that. Rather, the proof is in the water. In the past, Mars was a much warmer and wetter place. Now, Mars is still home to lots of water, mostly as vapor and ice, but in August 2018, a study published in Science, the 2018 study focused on an area at Mars' south pole called the Planum Austral, or Southern Polar Plain. Radar data from the ESA's Mars Express orbiter showed a 20-kilometer wide lake of liquid water at what they call the South Pole layered deposits. But that study just presented the subsurface radar data showing the liquid water and suggested that pressure and salt kept the lake from freezing. The authors didn't quantify the conditions required to sustain that liquid water. The new study, published by the AGU journal Geophysical Research Letters, pours water on the salt and pressure idea. The authors go further and state that without a magma chamber under the South Pole, there is likely no water there at all. There could be water there, but you'd have to explain it, and these guys did a really nice job of saying what is required and that salt is not sufficient. Jack Holt, Professor, Lunar and Planetary Laboratory at the University of Arizona. The debate around water on Mars has been ongoing for a long time. We've confirmed the presence of water, but now the debate is around how much, where, and in what form. And it's not all about whether we could somehow use the water on missions to Mars. It's more about understanding how planets form and evolve. It's also about how life might survive on other worlds. We think that if there's any life, it likely has to be protected in the subsurface from the radiation. Ali Bramson, Lunar and Planetary Laboratory, University of Arizona, co-lead author. We think that if there is any life, it likely has to be protected at the subsurface from the radiation, said Ali Bramson, a postdoctoral research associate at the Lunar and Planetary Laboratory at the University of Arizona and co-lead author of the new paper. If there are still magmatic processes active today, maybe they were more common in the recent past and could supply more widespread basal melting. This could provide a more favorable environment for liquid water and thus, perhaps life. Mars and Earth both have giant polar ice sheets. On Earth, it's common for liquid water to persist under ice sheets. Earth is volcanically active, and that heat prevents the subsurface water from freezing. The 2018 paper drew a parallel between terrestrial ice sheets and Martian ice sheets and the liquid water under them, but didn't answer the question of how the water got there. We thought there was a lot of room to figure out if the liquid water is real, what sort of environment would you need to melt the ice in the first place? What sort of temperatures would you need? What sort of geological process would you need? Because under normal conditions, it should be too cold, Sori said. To begin with, Bramson, Sori, and the other authors of the new study assumed that the detection of the liquid water under the South Pole was correct. Then they figured out what parameters would be necessary to create that water. They modeled the necessary salt content and the necessary heat flow from the planet to create all that water. They found that salt alone wouldn't be sufficient. They proposed that additional heat would have to be coming from the planet's interior, and the only obvious source of heat would be a magma chamber. The scarcity of food. Astronauts need to eat, and growing food on Mars would be a very difficult task. In fact, it would take several hundred years before farming could be conducted without protective greenhouses, since the soil there contains perchlorates, which are harsh chemicals that would need to be removed before any plants could be grown. Martian soil is devoid of the nutrients found in Earth soil and is also fine, meaning water would likely seep through it much more quickly than it would on Earth. Using human poop or other fertilizers could provide a quick boost of nutrients, such as nitrogen, and may also change the texture of the soil so it would cling to water longer, said Sokolov, who was a crew member last year at the Mars Desert Research Station in Hanksville, Utah. Earthly soil gets its nitrogen from the atmosphere, though atmospheric nitrogen is in a form that is not easy for plants to use. To transform nitrogen into a better food for plants, bacteria fix it. On Earth, a lot of nitrogen in our soil is fixed by bacteria that reside in the roots of various plants, like legumes, Sokolov told Live Science. In the long term, you would want a way to fix nitrogen to the soil there. Martian soil is also laced with nasty chemicals called perchlorates, which would have to be chemically removed for plants to grow there. And then there's gravity. Mars has about 1/3 the gravity of Earth, though experiments have shown that some plants can grow relatively normally in microgravity on the International Space Station. There's really no way to mimic the gravity light of the red planet. A 2014 study in the journal PLOS One showed that tomatoes, wheat, cress, and mustard leaves grew particularly well and even flowered and produced seeds in simulated Martian soil for 50 days without any fertilizers. In fact, these hardy plants grew even better in Martian soil, or regolith, than in nutrient-poor river soil from Earth. To determine what food ingredients to actually bring to Mars, scientists must balance trade-offs among the nutritional density of a crop, the resources required to grow them, and the germination time. Scientists may be growing lettuce on the ISS as a demonstration, but man cannot live on lettuce alone, Sokolov said. Instead, people have suggested crops such as radishes and strawberries as better Martian snacks, he said. Number crunchers have determined it would actually require less fuel to simply send over pre-made foods rather than the ingredients for farming for initial short-term visits, Sokolov said. Simulating Martian conditions. Before the Martian farming project gets going, humans would need to know a lot more about how plants will grow. That's part of the reasoning behind simulations of the Martian environment, such as the Mars Desert Research Station. Scientists there have grown everything from native desert plants to barley and hops in the station's simulated Martian soil. The soil, called Johnson Space Center Simulant 1, is produced using earthling rocks and soil based on Martian soil samples from 1970s-era Viking landers. And researchers at the University of Guelph in Canada are growing plants in low-pressure or hypobaric chambers to mimic the thin atmosphere of Mars. The team exposes plants to a host of rough conditions, including varying levels of carbon dioxide, pressure, heat, light, nutrition, and humidity to see which plants are hardy enough to survive Martian conditions outside a self-contained, air-controlled greenhouse, the star reported. Greening the red planet. Growing plants out in the Martian elements and not in a temperature and air-controlled greenhouse would be much more challenging, Sokolov said. Some people have said we should make Mars more like Earth, Sokolov said. That's not something to be taken lightly. It's in the realm of science fiction for sure. And even if people decided it's ethically acceptable to terraform Mars, it would be hundreds of years before the thin Martian atmosphere could be transformed into an oxygen-rich cradle for life. To build up that atmosphere, explorers would need to seed Martian soil chock full of oxygen-producing cyanobacteria, lichens, and microbes. It would take hundreds of years for them to produce enough oxygen and nitrogen for an atmosphere. That's still not too shabby, considering it took hundreds of millions of years for Earth's oxygen levels to stabilize. While the microbes were busy creating an atmosphere, solar wind would constantly be blowing that atmosphere away, because Mars lacks a magnetosphere, a magnetic field to shield the planet from solar radiation, he said. Even if people could figure out how to generate atmosphere faster than it dissipated, Martian winters can be a bone-chilling minus 207 degrees Fahrenheit, minus 133 degrees Celsius. It's possible that people could tailor an atmosphere with greenhouse gases that trap heat, but Mars is simply farther from the sun than Earth is, so it would still likely be colder than our planet on average, Sokolov said. Permanent spacesuits would be needed. Mars' atmosphere is not suitable for human life. For humans to live and work there, they will need the protection of a full bodysuit, not unlike that worn by the astronauts who walked on the moon during the Apollo program. The Mars suit must be flexible enough to allow the astronauts to work with both cumbersome construction materials and sophisticated machinery, and at the same time keep them safe from the harsh atmosphere. Why is the Mars atmosphere not suitable for human life? The air pressure on the surface of Mars is equivalent to that of Earth's atmosphere at 25 kilometers altitude, so too thin to breathe. Even if there was enough air pressure, there would be too much carbon dioxide and too little oxygen for humans. The Viking Orbiter infrared thermal mapper suggests that the warmest temperature may be 27 degrees Celsius, 81 degrees Fahrenheit, and the coldest minus 143 degrees Celsius, negative 225 Fahrenheit at the winter polar caps. Actual temperature measurements from the Viking landers range from minus 17.2 Celsius, 1 degree Fahrenheit, to negative 107 degrees Celsius, minus 161 Fahrenheit. A human civilization may not be difficult to initiate. To build a sustainable presence off Earth, humans will first have to answer some tricky questions about basic biology. Fast forward to several decades or half a century from now, and it's not inconceivable that humans could be living on Mars, building habitats, trundling around in rovers, mining the subsurface for resources, and producing the first generation of bipedal Martians. Except no one really knows if humans can successfully reproduce in space, whether that's during spaceflight or on another planet. To be clear, having sex in much lower gravity is a simple physics problem, but a host of unknowns swirl around about how space environments affect the actual biological sequences of events that must unfold with precision for a new human to grow, from fertilization to weaning. It's not as though we haven't tried to sort it out. Mice, rats, salamanders, frogs, fish, and plants have been the subjects of experiments looking at how spaceflight affects reproduction. To put it simply, though, the results so far are mixed and inconclusive. All of our big tech gurus out there who want us to be a multi-planet civilization, this is a key question that no one has answered yet, says Baylor College of Medicine physician Chris Leinhardt, who specializes in space medicine. Everyone is focused on the hardware, and the hardware is great, but in the end it's the squishy meat sack that messes everything up. Ignoring the human system, if you will, in future plans and designs is only going to lead to failure. Landing and returning to Mars. Landing on Mars will not be a smooth ride. For example, when NASA's InSight spacecraft entered into the atmosphere on Mars, it was moving at a whopping 12,300 miles per hour. While it was descending through the atmosphere, it had to slow down to just 5 miles per hour before landing on the surface. The deceleration happened in less than 7 minutes, which NASA engineers referred to as 7 minutes of terror. Engineers and scientists at NASA's Jet Propulsion Laboratory in Pasadena, California, are working hard this weekend preparing for another daring attempt to land a spacecraft on the surface of the planet Mars. The InSight spacecraft, designed to study Mars' interior, is scheduled to land on Monday, November 26, 2018. Details on how to watch here. It'll be NASA's 10th Mars landing attempt, and NASA has been mostly successful. But because of its thin atmosphere, Mars overall has a much lower success rate for spacecraft landings than the Earth, the Moon, or Venus. And along with other nations of the world, NASA has had its failures. And that's why Thomas Zurbuchen, Associate Administrator for the Science Mission Directorate at NASA headquarters in Washington, said late last week in a statement, "Landing on Mars is hard. It takes skill, focus, and years of preparation." No doubt about it, Monday's Mars landing attempt will be a nail-biter. Consider the speed at which the craft has to hit Mars' atmosphere and then, in a very short time, slow down enough to land. When NASA's InSight spacecraft hits the top of the Martian atmosphere on Monday, it'll be traveling at 12,300 miles per hour. That's 19,800 kilometers per hour. During its descent through Mars' atmosphere, it needs to slow down to 5 miles per hour, 8 kilometers per hour, about a human jogging speed, before its 3 legs touch down on the Martian soil. That extreme deceleration has to happen in just under 7 minutes, a time frame known to NASA engineers as 7 minutes of terror. In that 7 minutes, the InSight lander has to deploy its parachute and landing legs, spot the surface with radar instruments, and fire 12 engines to help it slow down. All of these actions are pre-programmed because, due to the finite speed of light, NASA engineers can't make changes to the procedure if something goes wrong. They can't even track the descent in real time. In fact, traveling at the speed of light, 186,000 miles per second, about 300 kilometers per second, signals from the InSight craft will need about 8 minutes to reach Earth. That means that by the time NASA engineers and the rest of us learn that InSight has reached the top of Mars' atmosphere, the lander will have already touched down safely or crashed. InSight stands for Interior Exploration Using Seismic Investigations, Geodesy, and Heat Transport. It's the first mission designed to study the deep interior of Mars. InSight blasted off from Vandenberg Air Force Base in Central California on May 5, 2018, and so far, engineers have described InSight's flight to Mars as uneventful, but, said Rob Grover about InSight's entry, descent, and landing, "There's a reason engineers call landing on Mars 7 minutes of terror. We can't joystick the landing, so we have to rely on the commands we pre-program into the spacecraft. We've spent years testing our plans, learning from other Mars landings, and studying all the conditions Mars can throw at us. And if we're going to stay vigilant till InSight settles into its home, in the Elysium Planitia region." When NASA engineers look at Mars, they see a planet-sized Venus flytrap. It lures us with the promise of scientific discovery, but the moment we land there, gravity and a harsh climate will conspire to keep us stuck on the surface. And that's not an option. If the Martian holds one lesson for real-life space exploration, it's that the public won't stand for spending billions of dollars only to leave astronauts stranded on another world. The most crucial part of any NASA plan for visiting the Red Planet, arguably, is getting off it. The spacecraft that NASA would build to get the job done, the Mars Ascent Vehicle, represents a formidable engineering challenge. When fully loaded with fuel, it's too heavy to launch from Earth and land safely on Mars. Instead, the vehicle would need to be pre-assembled and sent to the Red Planet years before the astronauts arrive, where it would make its own propellant by squeezing it out of the thin Martian atmosphere. And after that, the MAV must be built tough enough to remain fully operational despite being pummeled by massive dust storms and punishing UV radiation. When the cramped vehicle does finally take off, It needs to sustain the astronauts for days as they maneuver to rendezvous with the orbiting vessel that will finally take them home. The Mars Ascent Vehicle will be a mission with a mission, a crewed spacecraft launched into orbit from the surface of an alien planet, and there's only one chance to get it right. Hauling all of our stuff to the Red Planet. A mission to Mars will be humankind's first deep space caravan. As many as 5 separate spacecraft might be needed to ferry the astronauts and their cargo to the Red Planet there and back again. NASA engineers are faced with the daunting task of landing a Mars Ascent Vehicle safely on the Red Planet, where it will manufacture its own fuel to bring the astronauts back home. Entering the Martian atmosphere is thick enough to produce frictional heating, but too thin for using parachutes to reduce the speed of an object as massive as the MAV and its lander. Some of that cargo can be broken down into smaller components and then reassembled by the astronauts upon their arrival. Not so the MAV. You don't want to be on Mars trying to bolt engines on in your spacesuit, essentially wearing mittens in a dusty environment, says Michelle Rucker, a system engineer at NASA's Johnson Space Center. In NASA speak, that makes the MAV the largest indivisible payload element on the mission, weighing an estimated 18 tons. To date, the most massive object that we've sent to the Martian surface is a 1-ton Curiosity rover. Landing an object on Mars, especially one that weighs several tons, is not as easy as landing it on Earth, where a capsule basically falls from the sky, relying on the atmosphere to reduce the speed of its descent. On Mars, where the air is 1/100th of the thickness of Earth's, there's just enough atmosphere to be a pain in the butt, but not enough to do anything useful for you, says Rucker. Or put another way, it will burn you up, but won't do much to slow you down. That's why NASA is developing technology such as the Hypersonic Inflatable Aerodynamic Decelerator, a massive cone-shaped inflatable heat shield that would also act as a braking system. The shield would deploy upon entering the Martian atmosphere, slowing the lander from hypersonic to merely supersonic speeds. At that point, rocket engines would kick in for a controlled landing. Here's the kind of math astronaut Mark Watney would do to make it work. The landing will burn up around 5 to 7 tons of propellant. When it comes time to take off from the Martian surface, the MAV will need 33 tons of propellant to break free of the Red Planet's gravity, push through its atmosphere, and safely ferry the astronauts and their scientific cargo into orbit, where they can rendezvous and dock with their Earth return vehicle. And that's too much to send ahead. The propellant will need to be manufactured on Mars. Living off the Red Planet. If expeditions to the Red Planet are going to have any chance of succeeding, they'll need to live off the land. By making fuel on Mars, NASA can shave several tons off the initial payload mass. And after the first mission is over, the equipment can be left on Mars to serve as a nascent infrastructure for expanded facilities to process not only fuel, but also water and air for future explorers. The engines of the MAV will be powered by methane and liquid oxygen, all the ingredients needed to make that fuel, carbon, hydrogen, and oxygen, can be found on the Red Planet if you know where to look. In theory, oxygen can be extracted from the Martian atmosphere, which is 95% carbon dioxide, CO2, and from liquid and frozen water, H2O, buried beneath the surface. The leftover carbon and hydrogen would be combined to make liquid methane. Drilling for water, however, would add an unwelcome element of uncertainty to an already difficult mission. Excavating and processing is a lot more complex than simply taking atmosphere from Mars. The other problem with underground water propellant production is that it drives you to land where you're pretty sure there's water, says Rucker. If you need to dig and you land somewhere where it turns out you're on top of bedrock, then all bets are off, she said. If hydrogen won't be extracted from Martian water, then Plan B would be to send a payload of hydrogen to Mars as seed stock for making methane. But for an initial mission, that idea is also off the table. Although hydrogen isn't heavy, it requires large tanks for storage that would take up a lot of precious space. We've got a lander design. It kind of has a flatbed deck on top, says Tara Paulsgrove, an aerospace engineer at NASA's Marshall Space Flight Center. Right now, the MAV is taking up most of the room on that deck. There's not a whole lot of room there for a hydrogen tank. NASA engineers could accommodate hydrogen tanks by making the MAV taller instead of wider, but increasing the height of the spacecraft is a scenario they'd like to avoid. They're concerned that if the vehicle is too tall, there's a greater risk of it tipping over after landing. And Rucker says a taller MAV could place a difficult physical burden on the astronauts. If one or more of them are incapacitated during the mission, then climbing a tall ladder is the last thing they'd want. Easy access needs to be a high priority. As such, the current plan envisions sending an ascent vehicle fully loaded with liquid methane and equipped with a chemical plant that would manufacture liquid oxygen from the Martian atmosphere. The process is expected to take 1 to 2 years. When the MAV's tanks are full, the human crew will be sent to Mars, secure in the knowledge that they'll have a gassed-up vehicle waiting to get them back into space. A private foundation called Mars One plans to send a crew of 4 to colonize the red planet by 2025. 5 of the would-be astronauts contemplate a possible one-way trip to Mars. But NASA engineers won't be ready to hang up any mission accomplished banners. One of the challenges is that we're going to use cryogenic propellants, says Rucker. Once you make your propellant on Mars, then you've got to keep it cold for a couple of years before you actually use it without it boiling off. We've got propellants, and right now we don't have any valves that have zero leakage, adds Paulsgrove. You've got to think about that, which is why we're prioritizing technology development in the area of low leakage valves. More broadly, engineers are concerned that time is not on their side. The MAV will require 1 to 2 years to manufacture its fuel. Then the human crew will spend 200 to 350 days traveling to Mars, followed by their exploration of the red planet, which could last up to 500 days. Add it all up, and that means the MAV must remain operational and ready for takeoff for as many as 4 years after its initial landing on Mars. It's been sitting in the Mars environment, says Rucker. It's sitting in dust. There's intense UV radiation. How does your patio furniture look after it's been sitting outside for that long? And that's on Earth, where it gets considerably more protection than there.